Hello everyone. Today I'm going to discuss the second part of bearing capacity and foundation. In this lecture I'm going to discuss Prandtl analysis, types of shear failure and Terzaghi bearing capacity theory. So let's discuss the Prandtl analysis. So in this figure I have mentioned a strip footing. A strip footing is given that is resting on the ground surface. So in 1921, Perennial gave a theory for the penetration of punches into the metal. So same theory we use for the analysis of soil or to get the ultimate bearing capacity of soil for the strip footing, which is resting on the ground. So there is an assumption that a strip footing placed on the ground surface sink vertically downward into the soil at a failure, like a punch. So in this, in the next coming slides, in the coming slide you will see there I will discuss the types of shear failure. So punching shear failure is one of the type of shear failure. So in this case, there is an assumption that strip footing placed on the ground surface sink vertically downward into the soil at a failure, like a punch, like a punching shear failure. So in this figure, that is soil which is below the strip footing or near the strip footing, so divided into three zones. Zone 1, which is immediately beneath the strip footing. Zone 2, which is adjacent the zone 1, and zone 3, which is in between the ground surface and zone 2. So this zone 2 from the left side and right side, you can see in the figure, their behavior are same. Similarly, zone 3 in the left side or right side, their behavior are same. So when the strip footing starts sinking in the soil, so in the zone, whatever the soil in the zone 1, subjected to a compressive stresses, and at the footing, when the footing sink in the soil, so zone 1, which is subjected to the compressive stresses, apply pressure, exert a pressure on the sides zone 2 and 3. Means when the strip footing sink vertically downward, then zone 1 subjected to a compressive stresses. So by which the zone 1 exert a pressure on the side zone, like 2 or 3, on the side zone 2 and 3, exert a pressure. In this case, there is another assumption also that soil zone 2, the soil which is in zone 2 are in the plastic equilibrium. Right? And then the zone 2 pushes the zone 3 upward. So the whole phenomena is like that. The strip footing when sinking downward, vertically downward, so zone 1 feels a compressive stresses, and then zone 1 exert a pressure on the zone 2 and 3. In this case, zone 2 is in plastic equilibrium condition, and then zone 2 push the zone 3 in a vertically upward direction. Like, so you will see zone 3, when the pressure is developed zone 3, so you will find a curved shape near the foundation. Okay, and Prandtl developed the expression for the ultimate bearing capacity for the strip footing, assuming that the curved part of the slip surface, the curved part of this zone 2, curved part of the slip surface of shape of logarithmic spiral, So there is other assumption also. So finally there is expression for purely cohesive soil, ultimate bearing capacity at the surface is equal to 5.14 cu, where cu is the undrained cohesion of a soil. Are you getting my point? Okay. And then in this case, the bearing capacity, ultimate bearing capacity at the surface, it does not depend upon the width of foundation, width of footing, means which is independent of width of footing. So ultimate bearing capacity for the footing at a depth df below the surface also we can calculate by using this relation. Q is equal to 5.14 cu plus gamma df, where the gamma is the unit weight of soil which is below the footing, df is the depth of foundation, cu is the undrained cohesion of a soil. So these are the two formula that by using that we can calculate the ultimate bearing capacity at the surface for the strip footing. We have taken the assumption that there is a strip footing. But one more disadvantage of this theory, that this theory is valid only for the footing with a perfectly a smooth base in contact with the soil. Smooth base in contact with the soil. But in the real cases, actual footing we will see there is a rough base. Means this theory does not give the accurate results for the field condition. That's why in the 1943, Terzaghi has given some theory to calculate the ultimate bearing capacity for the strip footing. Right? Types of shear failure. So there are three types of shear failure. The first one is the general shear failure, and the second one is the local shear failure, and the last is the punching shear failure. So in the figure of A part of this figure, see there is a graph between the intensity, load intensity. Load intensity means load per unit area, or between the settlement. So load intensity is plot on the x-axis, and settlement is plotted on the vertically negative of y-axis, vertically downward. Okay. So for the first case, general shear failure, we will see that when you are increasing the load, settlement it is increasing, but at a certain value of Qu, that is the ultimate bearing capacity, if we can say, but that is the certain value of Qu, so at which you can see the settlement is increases suddenly. So a shear failure occur in the soil at that load, at the load Qu, and the failure surface extended to the ground surface. Means you can see at the ground surface, you can see, so there is a failure surface. Means failure surface will extend up to the ground surface. So this thing you can understand by this load settlement curve. So when you are increasing the load intensity, settlement is increasing, or at a certain value of Qu, you will see in the figure the settlement is suddenly increased. Means this is the case of shear failure. At that point, soil get failure due to shear. So this value of load intensity, that is Qu, is called ultimate bearing capacity of a soil. So a heave on the sides is always observed in the general shear failure. Always, because in this case, in the general shear failure, in this case, failure surface always extended up to the ground. In the second case, when local shear failure. So in this case, you can see the figure is also plotted between the load intensity, load per unit area, to the settlement of the foundation, settlement of the footing. So in this case, when you are increasing the load, where you are increasing the load from 0 to some value, so what you will see at the value of Qu1, that is less than Qu, means in this figure you can see Qu1. So at this value of load intensity, or this value of load, you will see there is a foundation movement. So at this value of Qu1, there is a foundation movement is happening with a sudden jerk. So what will happen, where again you are increasing the load, this will, where the failure surface will extend up to the ground surface. And at the value of QU, that is greater than QU1, so at the value of QU, we will see that failure surface extended up to the ground. Right? So this value of QU is also called ultimate bearing capacity for the local shear failure. This is called local shear failure. In this case also, failure surface is extended up to the ground. In this case also, failure surface is extended up to the ground. And in the figure you can see that at the value of QU1, that sudden jerk, foundation movement is happening due to the sudden jerk, and that is again when you are increasing the load intensity, then this failure surface is extended up to the ground surface, and that is shown in figure by the dotted line. In the first figure, general shear failure, we will see there is a continuous line, but in the case of local shear failure, we will see from the zone 2 it is a dotted line, dotted curve line. So this types of failure is called as a local shear failure. A heave is only observed, a heave is also observed in this case, you can see in the case of local shear failure. Right? The third one, that is punching shear failure. In this case, failure surface does not extend up to the ground surface. When you apply the load on the loose sand on soft clay, so in this case failure surface do not up to the ground surface. It cannot be extended up to ground surface. Only you will see that foundation is getting sink inside the soil. Only there is a vertical movement. So the footing fails at a load QU. That is, see in the second case, that is local shear failure, and in the third case, punching shear failure, you will see the graph is more or less similar. But that is not similar. This value of Q is very less as compared to local shear failure. So there is also a jerk in the foundation at a load of QU1, that is less than QU. So the footing fails a load QU at which the load settlement curve becomes steep and a particularly linear. So as compared to the local shear failure, punching shear failure, the slope between the intensity and settlement will be a steep slope. So general shear failure is generally happening in the case of dense sand or a stiff clay, and the local shear failure is generally happening in the case of medium sand and soft clay. Medium sand and a clay, not soft clay, and a clay. And punching shear failure is happening in the case of soft clay. Right, so these are the three types of shear failure, which is very important. So you will see, like, we are not constructing a foundation or a footing in a case of soft clay. We are not doing that. It means that punching shear failure will not happen if we are not going to construct. So that's why we will see the Terzaghi theory in 1943 has given to calculate the ultimate bearing capacity for the case of general shear failure or for the case of local shear failure. He does not given the theory for the punching shear failure, because we are not going to construct a footing in the loose sand or clay, soft clay, right? So these are the basic three types of shear failure. So now I am going to discuss the Terzaghi bearing capacity theory. Terzaghi in 1943 has given the theory to calculate the bearing capacity of soil under the strip footing. There are some assumptions which is important in the case of Terzaghi bearing capacity theory. So these are the assumptions in the case of Terzaghi bearing capacity theory. So in the figure you can see there is a strip footing. Their width is B, which is mentioned by the capital B. Load intensity is coming Q, U. Okay, at the footing, at the base of the footing, and again the soil is divided into three zones. Zone 1, which is in the elastic equilibrium, zone 2, and zone 3. So in this case, that zone 1 is itself behaving like a footing. It's behave like a part of footing. So what is happening? Zone 1 is exerted pressure on the zone 2, and the sloping edges AC and BC. See in the figure, AC and BC of the wedge CBA, which is zone 1, bear against the radial shear zones CBD, CBD and CAF, that is zone 2. So the curve CD and CF are the arc of logarithmic spiral. In the Prandtl analysis also, the curve of this in the of zone 2 was the logarithmic spiral. So in this case, that is same. Okay, so the curve CD and CF are the arc of logarithmic spiral. So two triangular zone BDE and AFG are the Rankine passive zone, that is zone 3. Okay, so again I am repeating this. Zone 1, that is wedge ABC, zone 1 is in elastic equilibrium. Zone CBD and CAF, that is zone 2, bear against that sloping edge AC and BC, that is mentioned in the figure. AC and BC of the soil wedge CBA bear against the radial shear zone CBD and CAF, that is zone 2, and the curve CD and CF are the arc of logarithmic spiral. So the two triangular zone BDE and FG are the Rankine passive zone, that is zone 3. And an overburden pressure is applied on the surface which is parallel to, or which is horizontal, or which is passing through the line AB. A overburden pressure is applied, that is gamma dF. So this gamma dF is gamma is the unit weight of soil and dF is the depth of foundation. So the failure zone will not cross this line. This line means whatever the horizontal line which is passing through the line AB. So the failure zone will not cross this line. Means it will not cross above the line GABF. Above the line GABF. It means whatever the shear strength of soil located above the soil is neglected. Whatever the soil which is above the horizontal line or above this horizontal GABE, the shear strength of soil is neglected. So that's why we are counting a overburden pressure, or we are taking the overburden pressure, that is gamma dF. Arc of logarithm, already I told you. The two trigonometric zone BDF and FG are the Rankine passive zone, zone 3. See, so when we will say the failure is occurred. So when we will say the failure is occurred. So in the figure that is mentioned, AC and C, there is a sloping edge, AC and CB. AC and CB of the soil wedge is equal to the upward pressure. So whatever the failure occur when the downward pressure exerted by the loads on the soil adjoining the inclined surface CB and AC of the soil wedge is equal to the upward pressure. So whatever the downward force which is coming by the load and weight of this zone 1 or weight of the wedge ABC. So whatever the vertical pressure developed at a sloping edge AC and BC, or we can say ACA and CB is equal to the upward force. So it means downward force and upward force is equal for the inclined slope AC or inclined edge AC and BC. So it means failure will occur. Means sliding movement will occur through the slope AC and BC. Are you getting my point? AC and BC are the edge of zone 1. Okay. So what is the downward force? Means we are saying like that failure will occur when the downward force will be equal to the upward force for the sloping edge AC and BC. So what is the downward force? So here the downward force will be due to the load that is coming from the column and footing, QE into B, QE the load intensity at pressure, or we can say the pressure at the base of the footing. So QU into B, the force. The length perpendicular to this figure is 1. So the force QE into B into 1. So I have written QU into B. So this weight is coming due to the load, and the second is the weight of the wedge ABC, or we can say the weight of the wedge or weight of the zone 1. So downward force are coming on the sloping edge AC and BC due to the two force. One force through the vertically external load, that is Q. If the Q total Q, if that Q is applied on the column, so the column will apply it on the pressure on the footing. So this footing pressure QU. So in the terms of force we can write Q into B into 1, means QU into B. And the second force will come on the sloping edge due to the weight. Weight of what? Weight of this wedge ABC. So weight of wedge ABC we can write 1 by 4 into gamma B square tan phi. How we can write? So what we can do, just calculate the area of triangle ABC or into length 1. So it will be a volume of this wedge and multiply with the unit weight of soil. This unit weight of soil, what is the unit weight? So the gamma is the unit weight of soil which is immediately beneath the footing. So we can write weight of the wedge ABC 1 by 4 into gamma B square tan phi dash. Where the phi dash is the angle of shear resistance, or in this figure angle CAB or equal to angle CBA equal to phi. Angle CAB will be equal to angle CBA equal to phi dash. That is angle of shear resistance. You can calculate also by trigonometry. We can calculate the weight of wedge ABC 1 by 4 gamma B square tan phi. And what is the upward force? These two forces are acting downward force at the sloping edge AC and BC. So what are the upward force? So upward force will be the vertical components of resultant passive pressure. The upward force are the vertical components of the resultant passive pressure, which is denoted by PP, and the cohesion acting along the inclined surface. So again there is two components in the which is couched for the vertically downward forces, and two forces also which is applying the vertically upward forces. So what are the two forces which is applying upward pressure on the sloping edge AC and BC? So these two forces are cohesion, whatever the shear resistance applied due to the cohesion, and the second one due to the passive pressure, the components of resultant passive pressure. So now we have the four force, which are two are vertically downward, which are two are in the. So we can write this equilibrium condition in the vertical direction. So we can write the equilibrium condition, or we can write this equation for the vertical direction. So see the first expression 1 by 4 gamma B square tan phi dash, that is the weight of that is vertically downward weight or force of the wedge of ABC plus QB into B. This is the downward force due to weight. So these two components are the downward force will be equal to upward force. So upward force there is two components. PP, which is acting on the vertically upward on the sloping edge AC and BC. So there are two on the AC and BC. So we can add PP plus PP. So we have written 2 PP, passive pressure. PP means passive pressure. Plus there is a shear strength which is inclined the surface. So we can write incline the slope AC and BC. So we can write 2 CD dash b by 2 cos phi dash into sin dash. Here the expression b by 2 cos phi dash is the length of sloping or length of inclined surface CB and AC or AC. B by 2 cos phi dash, it is the expression of length of AC, or we can say length of BC. So we have just equated in the vertical direction upward force or downward force, so we can get this expression. So when 1 by 4 gamma b square tan phi dash, this expression take right side of this equality sign, so it will become a negative of 1 by 4 gamma b square tan phi dash. Wait. This expression, the left side of this equality sign, 1 by 4 gamma b square tan phi dash, it will be QU. So left side of equality sign will be QU into B. This is wrong, I have written wrong here, okay. This will be QB into B will be equal to 2PP plus BC dash tan phi dash minus 1 by 4 gamma b square tan phi dash. So here the left side is QU into B, okay. So this expression of 2PP, that passive pressure, so the resultant passive pressure on the surface of CB and CA are made by the following three components. That is very, very important to understand that. We have to understand the three components, and these components are based on the assumption. So what are the three components? The first component produce the weight of the shear zone BCDE. BCDE. In the figure, you can see what is the BCDE. So, or in the case of this, when we are talking about the by weight of the shear zone, the rest one is neglected. So by assumption, taking the assumption that surcharge is 0 and cohesion of the soil is 0. And it means soil is a cohesion-less soil. So this weightage shear zone is produced only by the weight of the shear zone BCDE. Their surcharge is 0 and soil is cohesion-less. Right. Second, which is denoted by PPC. C means cohesion. So this is produced by the component C dash of the soil. By taking the assumption surcharge is 0 and soil is wetless, there is no weight, means gamma is 0. And third, which is denoted by the PP, which is denoted by the PPQ. Q generally we denote for the surcharge sometime. So produced by the surcharge by taking the assumption that C dash means soil is cohesionless and wetless. So PP, that is passive pressure, is made by the three components. So in this case C, gamma, C means which is showing the whether the soil is cohesionless or not. Gamma 0 or not 0, it means there is showing the soil is wetless or not. And the third one is the weight of the shear zone BCD. So at a time we have to take the we have to take the two value of this 0, like surcharge or cohesion, or surcharge and weight and surcharge and cohesion, whatever. And the third one, so means there is three component, and we are calculating pressure, passive pressure is developed by one of these component by taking the assumption two components and 0. And after that, then we can superimpose all these results by the weight or by the cohesion or by the surcharge, right? So more or less it will be same. So there is a error, some error, but we are neglecting the error, okay? So now at the place of PP we can write, PPW, PP gamma, it means due to the weight of BCDE zone. PPC, it means due to cohesion. By taking the assumption these two raised to are 0. And the third one, PPQ, by the surcharge, by taking the assumption there is a cohesion and weight is 0. So we can write this expression. So we have taken the assumption that weight, so we can write at the place of 2PP gamma minus 1 by 4 gamma b square tan phi, we can write B into half into gamma B into N gamma. Okay, so N gamma is some of the constants. Okay. Also we can write at the place of 2p pc plus bc dash 10 phi dash, we can write bc dash 10 nc. Or at the place of 2p pq, we can write b gamma df nq. So put all these value in the above equation, in the first equation, we can get this result. Or y we can write like this. So in the last expression you will see we have taken the common of b and then we just neglected. And just b is nullified from the both the side, then we can write qu, which is ultimate bearing capacity of a soil. C dash nc plus gamma df. See, in this case we have written at the place of b we cancel. Okay, so and the third expression is plus 1 by 2 gamma b into gamma n gamma. Also we can write, so at the place of C, in the last expression at the place of gamma df, we have written Q naught. So in this case, Q naught is the overburden pressure. Do not confuse with this. Q naught is the overburden pressure, and it will be not always equal to the gamma df. By taking the overburden pressure, you have to take care of gamma. Suppose soil is in the submerged condition, and you cannot take the value of gamma submerged into gamma df, into df. Okay, so by taking, see, Q naught is the overburden pressure which is on the zone third, So it will depend what are the soil is there available above the zone third, and that will be applied the overburden pressure. Okay, so by calculating the overburden pressure, you have to be sure that what the type of the soil is there above the zone third, right? So the last expression, that is Qu is equal to C dash Nc plus Q naught Nq plus 0.5 gamma B N gamma, which is called Terzaghi bearing capacity equation for a strip footing under the general shear failure. I have discussed in the previous slides 3 types of failure: general shear failure, local shear failure, and punching shear failure. So this equation is valid to calculate the Terzaghi bearing capacity for the strip footing under the general shear failure. So in this expression you will see the C dash into NC, that is due to the cohesion, Q naught into NQ, that is based on the surcharge, and the third expression, that is 0.5 B gamma B N gamma, that is based on weight. So suppose you are working on the surface, so it means surcharge will be 0. Suppose you are calculating the bearing capacity of soil for the only cohesive soil or for the purely cohesive soil. So the rest 2 components due to surcharge and the weight will be cancelled, and we can write Q naught Qu is equal to C dash Nc. Okay, so here the Q is the ultimate bearing capacity equation for the strip footing in the case of general shear failure, where Nc is Nc in terms of phi, that is written, where the Nq is given, and where N gamma is this. So this Nc, Nq, and N gamma, these are the constant, and this is called Terzaghi bearing capacity constant, or some other term also, but these are the constant, and this constant like Nc, that is depend upon the cohesion of a soil. Okay, that is belong to the cohesion, right? Nq, that is depend upon the surcharge. N gamma, that is depend on the weight. So there is also phi. Phi is the angle of resistance, shear angle of shear resistance. So in this equation only we have to take care of how we can calculate the overburden pressure, right? In where A is equal to e to the power 2 3 pi by 4 minus phi dash by 2 10 phi dash. Are you getting my point? Okay. So ultimate bearing capacity in the case of local shear failure. Once you have calculated the bearing capacity for the general shear failure. So by applying some empirical reduction formula, you can also calculate the ultimate bearing capacity for the local shear failure. So in the 1943, Terzaghi has given some empirical relation to calculate the ultimate bearing capacity at the case of local shear failure also. So for the case of local shear failure, we can apply mobilized cohesion C dash M, that is 2 by 3 C dash, and mobilized angle of shearing resistance, that is phi dash M, which is equal to 10 inverse 1, 2 by 3, 10 phi dash. So the equation for the local shear failure for the strip footing can be written by putting the value of C dash M at the place of C dash, and by putting the value of phi dash M at the place of phi dash, we can get this equation, where the NCQ, NQ, and N gamma are for the reduced value of phi dash M, that is equal to phi dash M. Right? Are you getting my point? Same formula we can apply, but at the place of C dash, in the case of local shear failure, at the place of C dash, we will apply C dash M. Or at the place of phi dash, we will apply phi dash M. So let's discuss some of the numerical problems. So the first numerical we have, a 4 meter wide strip footing is founded at a depth of 1.5 meter below the ground surface in a C5 soil as shown in the figure. The water table is at the depth of 5.5 meter below the ground surface. The soil properties are C dash, phi dash, gamma saturated, gamma bulk, and gamma W are given. The value of bearing capacity factors for the different phi dash are given below. Using the Terzaghi bearing capacity equation and a factor of safety, Fs is equal to 2.5, the net safe bearing capacity for the local shear failure of the soil. See, in this equation, we have to calculate the ultimate bearing capacity for the local shear failure. So first, for calculate the bearing capacity, in the case of local shear failure, we have to calculate the mobilized cohesion and mobilized angle of shear resistance. So for the local shear failure, mobilized cohesion, that is we have calculated, because we have the phi dash, so we have calculated the phi dash M, that is 20 degree. So for the 20 degree, we have the C, NC value, NQ value or N gamma is given, that is NC is equal to 17.7, NQ is equal to 7.4, and N gamma is equal to 5. Are you getting my point? We have to calculate, we have to see this NCQ, NQ or N gamma value not for the phi dash. For the local shear failure, we have to see the value for the phi dash M, that is mobilized angle of shear resistance. Mobilized angle of shear resistance. So the ultimate bearing capacity in case of local shear we can calculate by using the Terzaghi theory, or by using the Terzaghi equation which is mentioned in this equation. So all we have this value C, NC dash, NQ dash and N gamma dash for the local shear failure for the value of phi dash M. So we can calculate. So now we can calculate for the net ultimate bearing capacity by using this formula. We can reduce the overburden pressure from the ultimate bearing capacity, so we can get the value of 4746.2 kilonewton per meter square. Right, but we have to calculate the net say bearing capacity, and factor of safety is given, so we can calculate net say bearing capacity by using the factor of safety, so we can get the 298.48 kilonewton per meter square. So for the if the data is given we have to calculate the ultimate bearing capacity for the general shear failure, so we can directly calculate by using the phi dash and C dash. But if we have to calculate the local shear failure, ultimate bearing capacity for the local shear failure, so we have to go for the mobilized shear parameters like mobilized cohesion and mobilized angle of shear resistance. Right. Next question we have, a strip foundation is founded at a depth of 1.4 meter below the ground level. water table in the area at the ground level and the soil is cohesionless. The footing is to be designed to carry a net safe load of 460 kg per meter square with a factor of safety as a 3. Find the width of the footing under the Terzaghi general shear failure criteria. Here the criteria is mentioned, that is general shear failure. Assume saturated unit weight, gamma saturated is equal to 21 and the angle of internal friction of soil 36 degree. For the 536 degree, NQ is given 43.2 and N gamma is given 42.6. So you can see in the figure there is a load intensity is given 460 and footing is a strip footing, and the footing depth of foundation is 1.4 meter, and here the soil is a cohesionless soil. So directly we can apply the Terzaghi theory. So all the data which is given, just note down. So these are the data that is given in the question. So we can apply the Terzaghi theory. So according to the Terzaghi formula for the ultimate bearing capacity of a soil, so in this relation, the question is saying the C is equal to 0 because the soil is a cohesionless soil. So by putting the value of C is equal to 0, we can get this formula. So now we can put the Q naught. What is the Q naught? Gamma dF. So you can see the water table is at the ground level. So means whatever the soil which is above the base of the foundation or which is below the base of the foundation is in submerged condition. So gamma we can use, at the place of gamma we can use the gamma dash, that is submerged unit weight of soil. So submerged is nothing but gamma saturated minus gamma W, that is unit weight of water. So we can write 21 minus 9.81 and depth of foundation is given 1.4 and NQ is given 43.2. Again gamma is given, B is given, B is not given. We have to calculate the V. We have to calculate the width of foundation, right? So V is not given. N gamma is given 42.6. So we can calculate the ultimate bearing capacity in terms of B, that we get 665.28 plus 234.3 B. Okay, so now we can calculate the net ultimate bearing capacity by using this formula, like QE minus gamma D. Like we can detect the overburden pressure from the ultimate bearing capacity of a soil. But in this case, what is the gamma? Like what is the overburden pressure? So see, in this case we cannot write gamma submerged at the place of gamma. Like overburden pressure means whatever the soil just removed and whatever the pressure of that soil before the foundation, like we are going to excavate the foundation. So due to that soil, whatever the stress is developed at the foundation, at the base of foundation, that is basically the overburden pressure. So here the soil is in the saturated condition. So what is the overburden pressure? So overburden pressure is the saturated unit weight into the height or depth of the foundation, right? So at the place of gamma we can write gamma saturated. So gamma saturated into depth of foundation, that is 1.4 is given. So finally we got net ultimate bearing capacity of a soil 635.88 plus 234.3 B. Now we can calculate the net safe bearing capacity of a soil by using the factor of safety, that is given 3. So finally we get 211.96 plus 78.1 B, right? And load is given, load intensity is given 460 kN per meter square. So it should be less than or equal to net safe bearing capacity of a soil. So for calculating the width or for calculating the minimum width, we have taken the equality sign, like 460 is equal to 211.96 plus 78.1 B. So in this equation, only one is unknown, that is B. So we can, after solving this equation, we can get the value of B, that is 3.17 meter, right? So in this question, only one thing you have to remember. So what is the overburden pressure? So overburden pressure in the case of submerged condition of soil, it would be saturated into depth of foundation, right? You cannot write submerged unit weight for the calculation of overburden pressure, right? Overburden pressure means before the excavation of foundation, what is the total stress or what is the stress at the base of the foundation where you are going to construct the foundation, right? Okay, so these are the some references that I have taken. Thank you. In the next lecture I am going to explain the Terzaghi theory again for different for the different shape of footing, or for the different condition of water table, like water table below the foundation, water table at the base of the foundation, water table at the above the base of the foundation. So all these criteria I am going to discuss in the next lecture. Thank you.